Welcome back to Honors Calculus. In this video, we're continuing our discussion on logic and proofs with a couple of proofs on sets. So again, let me get my head out of the way and let's jump in. In the last video, we were looking at the natural numbers. And to start off today, we're going to extend that with the idea of the integers. The name of the integers is this blackboard bold or double stroke Z. And as you are already familiar, the integers are the positive and negative whole numbers. And so to define that, we're going to look at three properties. We start by defining this idea of 0 as an integer. And we, of course, want all of the natural numbers to be integers as well. So we'll define the integers by saying that the natural numbers are a subset of the integers. We'll introduce this idea of 0 because it's useful to us. And then the third property, the integers are useful because of the way that positives and negatives behave. And we describe that by saying that if n is an element of the integers, then the opposite of n is also an element of the integers. So we have positive and negative numbers. And since every natural number is an element of the integers, then the opposite of every natural number is going to be the negative number that pairs with it, and now we will have all of the positive and negative integers. Next up, I want to look at something that seems obvious at first glance. And that thing is set equality. What does it mean for two sets to be equal to each other? There are a couple of ways you can define set equality, but the one that is the most useful in studying sets and analyzing sets is this idea of subset inclusion. Sets A and B are defined to be equal to each other if and only if both A is a subset of B and B is a subset of A. If both of those subset inclusions are true, then you have set equality. And this is useful to us because it is far easier to show subset inclusion than it is to show directly set equality. To show what I mean, let's take a look at a couple of examples. Let's let set A be the set of all 4k plus 1 such that k is an integer. And let's let B be the set of all 4k minus 3 such that k is an integer. And our claim is that these two sets are in fact equal to each other. And we would like to prove this claim. Use what we know in order to establish that this must be the case. Right? What do we know? We know the definition of set A, we know the definition of set B, and we know that we've defined two sets to be equal to each other if and only if the subset inclusions in both directions work out. So that's what we have to do. So let's first pick a number n out of set A. And our goal here is to show that A is a subset of B. So we pick a value in A, and our goal is to show that it is also in set B. Right, the definition of set A, let's try that again with actual characters that look like mathematical symbols. Right, so we pick n in A, and the definition of set A says that there is some k in the integer z such that st is an abbreviation for such that n equals 4k plus 1. Right, that's the definition of n in A. Now, I'm going to be creative. Because I can take 4k plus 1 and I can add 4 and subtract 4 at the same time without changing anything whatsoever. Mathematician's favorite tool. Invent something whole cloth and just to stick it in, right? We can't arbitrarily add 4, we can't arbitrarily subtract 4, but if we both add and subtract 4, we haven't actually done anything. Now let's take that and group things. So we have 4k plus 4, and we have negative 4 plus 1 as two separate groupings. 4k plus 4, we can factor out a 4, and negative 4 plus 1 is the same thing as negative 3. All right. Now we have this new thing here called k plus 1. And I don't know anything specifically about k plus 1, but I know one of the nice properties of the integers is that when you add a number to a natural number, it's still in there. So adding 1 to an integer should still be fine. K plus 1 is a new integer. Right, so this thing doesn't look like 4k plus 3, but this is definitely 4 times something minus 3. And that's the definition of B. Right, 4 multiplied times some integer and then subtract 3, That's what it takes to be something in B. And so by picking an arbitrary element out of set B, we show that that element must, picking an arbitrary element out of set A, we show that that element must be in set B, and so A is a subset of B. Now we're getting somewhere. Now I want to do the same thing the other direction. Remember, set equality is subsets both ways. So we showed that A is a subset of B. Now let's repeat this whole process and show that B is also a subset of A. To show that I'm picking something different, let's switch from calling it N to calling it M. And let's pick some M in B. Right, and the definition of B is that everything in B is some 4 times some K minus 3. We've already used K, so just to not reuse letters, I'll switch to the next letter, L. So M is 4 times L minus 3. But we can make the same tricks that we used before. I can arbitrarily add and subtract something. In this case, I'll subtract 4 and also add 4. And I'm doing that because in my first grouping here, 4L minus 4, there is a common factor of 4 I can bring out, and that leaves behind L minus 1. And in my second grouping, 4 minus 3 is 1. So just like we saw before, we have 4 times something plus 1. And since L is an integer, sliding that up the screen a little bit, since L is an integer, L minus 1 is also an integer, so we have that M here is 4 times some integer plus 1, which is exactly the definition of set A. And this time we took a random element out of set B, we showed that that thing must be an element in set A, and that's enough to conclude that B is a subset of A. We showed that A is a subset of B. We showed that B is a subset of A. And since we have subset inclusion both directions, that means that we have set equality. All right. So there's one interesting property of sets. Given two sets, we can use this technique of identifying subset inclusion to prove that the two sets are in fact equal. Of course, if they are equal. The next property that I want to look at is called closure. A set is called closed under some operation if, when you take any two elements out of the set and you perform that operation on those two elements, the result is also in the set. I don't have the time to show that we have some closure properties in the sets we've talked about so far, the natural numbers, the integers, and the rationals. Honestly, showing that that's the case is not going to be important to us. What is interesting to us is seeing what happens when something is not the case, right? The natural numbers are closed under addition and multiplication, but not subtraction or division. Right, the natural numbers aren't closed under subtraction because 3 minus 7 is -4, which is not a natural number. And 15 divided by 2 is 7.5, which is also not a natural number. And in algebra coursework, you generally see that the big advantages, the reason that we go to the integers, is that the integers are closed under addition, subtraction, and multiplication, but not division. And then the rationals are closed under all four: addition, subtraction, multiplication, and division. And for all intents and purposes, everything that you have studied in algebra can be done using just the rationals, everything involving addition, subtraction, multiplication, and division. When you start getting into higher order things, right? Square roots stopped falling into the case. You started looking at exponential and logarithmic functions where you need the natural base e. You started looking at trigonometry where you need the circle constant pi. And of course, geometry also where you need some of those things. That's where the rational numbers break down. And so, generally, at this point in a course, in an algebra class, your instructor will say something like, there's a bunch of other numbers that aren't rational that are still very important. We call those things the irrational numbers, and bringing everything together, we get the set of real numbers. And it's really incredibly hand-wavy. Next time, in lesson 1, we're going to use the idea of inequality to get most of the features that we need to clearly define the real numbers. Although I will tell you now that we're not going to get entirely all the way there. We're going to get most of the way there. Much later in the course, actually in Unit 2, after the first exam, we will look at one last property of the real numbers and finally be able to have a formal definition of what the real numbers actually are. Things to look forward to. For today I'm going to leave you with one more problem for you to try on your own. And this is going to look similar to the first example we did. Let's take a look at a couple of sets. Let's call set M the set of all 5x minus 3. Actually, we should make that k. Let's stick with the same sort of thing we were doing before. Let's call that 5k minus 3 such that k is an integer. And let's let set big N be the set of all 5k plus 2 such that k is an integer. And your task is to prove that these two sets are in fact equal to each other. So, see what you can do with that, write out your work, and I'll see you in the next video.